In this chapter, we're going to explore how the fundamental design of a web application, its architecture, can actually be its greatest weakness. We often focus on hunting down individual bugs in the code, but sometimes the most devastating vulnerabilities are hiding in plain sight, right in the very blueprint of the system.
So we're going to step back from those individual coding mistakes and look at the bigger picture. We're going to examine how the very structure of an application, the way its different parts are connected, and, more importantly, how they trust each other, can be systematically taken apart by an attacker.
So here's our game plan. We'll start by defining what this architectural battlefield looks like. Then, we'll dive into how attackers compromise these systems and, just as importantly, how we can build robust defenses. We'll also look at the unique challenges of shared and cloud environments, and then we'll wrap it all up with the key lessons you should take away.
Okay, let's get right into it. To really understand how to attack an application's architecture, we first need to get a handle on how modern applications are built. And the most common pattern you'll see out there is something called a tiered architecture.
The easiest way to think about this is like a medieval fortress. You've got your outer wall, that's the presentation layer that the user sees and interacts with. Then you have the inner courtyard, that's the application layer, where all the real thinking and business logic happens. And finally, you have the central keep, the most protected part. That's the data layer, where the crown jewels, all your information, are stored. Each layer, in theory, should provide its own distinct line of defense.
So at its core, most applications you use every day follow this simple three-tier model. But of course, in the real world, big, complex systems can have many, many more layers. You might have dedicated application servers or special tools called object relational mappers that help the code talk to the database. Each one of these becomes another link in a much longer chain.
All right, so we built our fortress. Now let's switch gears and put on our attacker hats. A tiered architecture seems pretty secure, right? But what attackers are really good at is finding the weak links between these layers. They exploit the assumptions that developers make about how these different tiers are supposed to interact.
There are really three main ways an attacker can go after the architecture. For our purposes, we're going to focus on the first two, exploiting trust and subverting tiers. Why? Because these two really get to the heart of fundamental design weaknesses that are just incredibly common out there in the wild.
So, what's the core issue here? It all comes down to a single dangerous word: trust. What happens when one tier gets breached? Well, very often the other tiers are designed to blindly trust it. For example, the database server just assumes that the application layer has already checked who the user is and what they're allowed to see. So, if an attacker finds a SQL injection flaw in that application layer, they can send a malicious command and the database just runs it, no questions asked. That trust relationship becomes a superhighway for the attack.
Let's make this real with a concrete example of subverting tiers. Imagine a really common setup: a single server running Linux, Apache, MySQL, and PHP, what we call a LAMP stack. This application has a totally harmless-looking feature that lets a user choose a different skin or theme for the site, and all it does is show them the contents of the right CSS file.
This is where a simple little bug known as a path traversal vulnerability becomes absolutely critical. If the application doesn't properly check the file name, an attacker can use these .. sequences to basically tell the server, go up one directory. Do that enough times, and you can navigate right out of the web folder and request any file on the entire server. And the key architectural failure here is that the tiers aren't properly segregated. A bug in the web layer now threatens the entire machine.
And here's the punchline. This brilliantly illustrates the catastrophic result. The attacker used that flaw in the presentation tier to jump sideways and read the MySQL user file directly from the disk. They have completely bypassed the database's own access controls. Think about that. The database tier security was just rendered totally useless because of a flaw in a completely different layer of the application.
Okay, let's level up to an even more advanced attack that chains two separate weaknesses into one. In a lot of PHP applications, user session data, like your username or preferences, is just stored in simple text files on the server. So if an attacker can control some of that data, like setting their nickname, and there's also a separate bug called a file inclusion vulnerability, they can achieve a full compromise. That file inclusion flaw is a bug where you can trick the application into running a file it was never supposed to.
Let's walk through it. First, you can see the attacker setting their nickname to a tiny piece of PHP code. The server, not knowing any better, just saves this to their session file on the disk. Then, the attacker finds a completely different feature that has that local file inclusion bug. They use it to trick the server into including and executing their own session file as if it were code. The result? The server runs the id command and shows the output. The attacker now has a backdoor and can run any command they want on that server.
All right, that's enough doom and gloom. Let's switch back to defense. How do we design our fortress to actually withstand these kinds of attacks? The key isn't having one perfect, unbreakable wall. It's about making sure that if one wall is breached, the attacker is still contained.
So how do we build a secure architecture? It really boils down to 3 core principles that all have to work together. First, we have to minimize trust between our components. Second, we need to segregate them so they can't interfere with each other. And third, we have to apply defense in depth, which means adding security measures at every single level.
So what does that look like in practice? Well, minimizing trust means the database doesn't just blindly follow orders. Maybe it uses a special low-privilege account for just reading product data and a completely different, more powerful account for processing orders. Segregation means the web server's user account literally doesn't have the permission to read the database's files from the disk. And defense in depth means that even if an attacker gets in, the underlying OS is hardened and sensitive data is encrypted, which severely limits the damage they can actually do. Okay, now let's add another layer of complexity. So far, we've only been talking about a single application. But what happens in a shared hosting environment, where your application is running on the same server as dozens or even hundreds of other applications from different customers? Suddenly, your entire threat model changes. It's not just about defending against attacks from the internet anymore. Now you have to worry about your digital neighbors. A vulnerable or even actively malicious application sharing your server can become a launchpad for an attack directly against your code and your data.
For instance, a malicious customer could upload a simple Perl script just like this one. It's a tiny but incredibly effective backdoor. That first line grabs a command from the URL. The next line, the one with the backticks, actually executes it on the server. Once this is uploaded, that customer can run any command they want, and from there, they can almost certainly read the files and data of every other customer on that same machine.
Now, take that shared hosting idea and scale it up, way, way up. That's the cloud. Cloud environments are essentially shared hosting on a massive scale, but with even more complexity from things like virtualization and powerful web-based management tools that become huge targets themselves.
The cloud introduces some really unique attack vectors. For example, cloning virtual machines too quickly can sometimes cause them to share the same random number seeds, which can weaken their cryptography. But more critically, think about those web portals you use to manage your entire cloud infrastructure. That portal is now a single, high-value point of failure. A single vulnerability in that one management app could give an attacker the keys to the kingdom, exposing the entire infrastructure of thousands of companies. So how do we defend these massive, complex environments? The principles are actually the same, but the implementation has to be even more strict. Access must be tightly controlled with the least privilege possible. Each customer's code and data has to be rigorously segregated, ideally running in its own sandboxed account. And maybe most importantly, there can be absolutely no implicit trust. Data moving between internal components has to be treated with the same suspicion as data coming from a random user on the internet.
Okay, we have covered a lot of ground, from the basics of tiered architectures all the way to the complexities of the cloud. Let's boil it all down to the most crucial points you need to remember.
If there's one thing you take away from all this, let it be this. Security can't be an afterthought that you just bolt on at the end. It has to be woven into the very fabric of the application's design from day one. We've seen how a flawed architecture can turn a tiny bug into a catastrophic breach. And in today's world, where we all have digital neighbors, your security is only as strong as the foundation you share.
Every feature you use, every connection between systems, it's all part of a larger architectural story. The question you should be asking yourself now is that story one of resilience and security by design, or is it just a blueprint for a breach waiting for an attacker to come along and read it?